invitation. And, I'm very excited to give this talk. And the topic will be, as I mentioned, geometry, topology, and defects in the programmable assembly of nanoparticles. Those are the list of collaborators. I also want to acknowledge the experimental collaborators. I also want to mention that I am an editor of the computational material science, so I always use that to advertise the journal. We are always welcoming papers, especially in this area. So, just so that, and I want to also mention the workshop that we are organizing at the Kavli Institute for Theoretical Physics. This is a workshop that will be, that it will happen in this at Santa Barbara in 2023. This is the main page of the Santa Barbara Kavli Institute. If you go there to the events, you will see that this is the workshop that we are organizing. So you can all apply. Usually this is actually a 7-week workshop that goes from March 27th to May 19th. Usually we look for long-term applicants. Long-term applicants are those that stay for at least 3 weeks. We have a few short-term applicants but those are very hard because we have very little, and this is actually the presentation. So those are the topics. And just to mention that following the workshop, there will be a conference. The organizers of the conference the workshop are Michael Angle, which is one of the organizers of this talk, Laura Liu, Monica Olvera, Aaron Rabani, and myself. And the following conference will be organized by these people, which are all of them except me, because the lead organizer of the workshop does not take part on the conference. So with that, let me just go to the actual topic of the talk. One thing that I would like to mention is that we all know how to make materials starting from the elements. Yes, so we have a nuclei, we have electrons, these form atoms. These atoms are bonded, and then through this bonding you make materials or crystals, whatever you want. The thing is that we have now at our disposal a new periodic table where instead of starting with nuclei that are consisting of protons and neutrons, we start with a here nanocrystal. The advantage is that you have a much wider configurability than just the number of protons and neutrons. You can see here that you can have shapes, you can have chemical composition, you can have size, you can have all sorts of many different types of cores. And the role that the electron plays can be played by the ligands, so you have to functionalize these nanocrystals with ligands. And there are a huge range of different ligands at your disposal that you can combine with these nanocrystals, and in this way to make what we would call these big atoms, what is called the equivalent atoms. And then from here you can also have some sort of covalent bonding. And then from this covalent bonding, you can have you can make new materials. And here there is a review by Michael Angle where you can all these things are described. So let me just show you examples. This is an example of a binary superlattice where you have two types of nanoparticles, and this is what they look like. From electron microscopy, they have structures that are equivalent to other inorganic components like sodium chloride, gold, copper, etc. And you can see here that they also form quasicrystals, so as you can, equivalent, same way. So you have here a whole description of new materials which are made not of atoms, but of these nanocrystals, and their ligands, which is what determines the type of bonding that you have. So basically the idea here is just that you have a bunch of components, the nanocrystals, the ligands, etc. And what you want to do is somehow through thermal fluctuations and maybe by inducing some sort of directed assembly, go from something that is completely disordered to just form the structure that you want. And basically that revolves of being able to program all these interactions in such a way that you are able to form these structures. So and this is in a way the taming of the KVTs, and you can even go further. The idea being that you just go and make putting one nanoparticle here, another type, which is a conductor, semiconductor, and in this way design materials which can do many functions at the same time. And that's the plan of the talk. So this is actually something we've been doing for quite some time. And we started with DNA. So this was a pioneering paper by the work of Oleg Gang and Chad Mirkin groups, where they were able to assemble DNA-based nanoparticles by using complementary DNA. And we started developing theory. Then we started realizing that there were many other ways in which you can have nanoparticles to assemble. That is the process by which you grab them with hydrocarbons and then you assemble by solvent evaporation. And we've been working a lot on these things, and I will be describing some of these. Parallel to that, we started developing our own experiments. That includes nanoparticles that are grafted with polyethylene oxide or that you can assemble with diethol linkers. Then we started with the same group in the Ames lab. We started looking into other ways, but you can use complementary chains by interpolymer complexation. And then we were able to form these other types of nanocrystals by combining polymers that have complementary type of interactions. Recently, we've been looking at nanocomposite tectons, which is another variation on this topic. And also going back to the issue of assembly by solvent evaporation, we've recently started working in perovskites. This is one of paper that we recently published in Nature. And those are interesting in the sense that we are going beyond structure to just look into the functions that these nanoparticles have. So with in this talk, I will be just concentrating on this type of nanoparticles. I mean, there are many other topics that come with these other type of problems, but right now, this is what I will be describing. So here we start with, so what is the problem that we are describing? So we have binary nanoparticles. We have two types of nanoparticles, nanoparticle A, nanoparticle B. They are functionalized. There is a capping ligand that you attach to them. They are soluble in organic solvent, and then you put them like this, and then you just gradually, very slowly evaporate the solvent. And in this way, you end up with a superlattice, which is binary. There are two types of nanoparticles, and this is an example. Sodium zinc 13 is one of my favorites. It has a very large unit cell with 112 particles in each unit cell. So now the question is, how are we going to describe these systems? And obviously, you know, an obvious way to do it, I mean, that's what originally has been done, is to describe them with hard spheres. So these are the spheres. You can think of them as being billiard balls, yeah? So when you go to billiard balls, in that particular case, what you are looking is at the packing fraction, that is how much of the space is covered compared to the space that it is available. If you are looking in 2 dimensions, that would be a situation like that. And in this particular case, what you have a circle which has well, you have a circle which has area pi r squared, the actual all area is 2r squared, and then the packing would be 0.7853. So that would be your, the amount of packing fraction that you cover. Yeah, when you go in 3 dimensions, I mean, you probably in this audience knows that we have FCC, BCC, simple cubic, those are the type of packing fractions that you have. We are interested in binary systems. So in binary systems, what we have is we have like 2 types of spheres. And then you can see that you can improve on the packing fraction that you get by filling the interstitials with the smaller spheres, and that would give you a packing fraction that it is larger. But in general, this packing fraction will be a function only of the ratio of the 2 radii. So when you go and you plot the 3-dimensional case, what you get is a curve that, depending on the ratio of the 2 sizes, will give you packing fractions that look like that. So some lattices will improve on the packing fraction of single component FCC, which is the maximum packing fraction that you can have with single component particles, with just one type of particles. And then, you have these plots that show you, what are the packing fraction. One thing that you notice is that in general, if you're packing, the asymmetry between the 2 spheres is not very large, you cannot beat the packing efficiency of a single component. Okay, so how that relates to the experiment? Well, I mean, the way to relate it to the experiment is that what people typically do is that they put these nanoparticles on a 2-dimensional triangular lattice, and then they measure for each nanoparticle separately, and then you measure what is the lattice constant, and the lattice constant for this single component 2-dimensional triangular lattice gives you an idea what is the equivalent hard sphere diameter or hard sphere radius for this sphere. Then what you do is that you compute these 3-dimensional plots, and then you do an experiment, and you realize that there is a correlation between where the packing fraction is maximum and where experimentally these lattices are found. So for example, if you have a ratio of diameter, which is 0.8, well, typically you will get magnesium zinc 2, for example, which is the one that has the packing fraction here. And this is already something. I mean, it gives you that when you have a superlattice, you do these plots, and then it will tell you that if the superlattice exists, it should happen around the maximum of the packing fraction. But then when you look at this more closely, you start realizing that the correlation is not so great. Yeah. First of all, magnesium zinc 2 has packing fraction smaller than the single component. So the first question is, okay, if we are taking this seriously, why this system doesn't phase separate into different FCC lattices, each of the type of nanoparticle, which would give you a higher packing fraction? That's the number 1 question. The number 2 is that, as you see, if you take this seriously, you see that in this particular case, if those are packing of hard spheres, the packing fraction becomes very small, 0.5. That is a very open lattice, and you should be skeptical about the stability that such lattice should have. I mean, this is too much of open space. Yeah. So basically what we see is that there is an imperfect correlation between packing fraction and experiment. And in fact, I mean, people, I mean, by Bowles and Talapin have measured the packing fraction in the experiment. And you see that it is really very far from what hard spheres predict. So here you have the hard sphere prediction. Here you have what the packing fraction for the actual lattice, the experimental measure one is, and you see that there are big differences there. So the high sphere has some merits, but when you start taking a little more seriously, clearly fails to describe what the experiments find. So the next question is, okay, so let's just assume for a moment that we look, instead of hard spheres, we were allowing the spheres to be a little more flexible. So the idea would be a model where you have softer spheres. Well, I mean, you know, that's kind of a reasonable idea. After all, the ligands that form these nanoparticles are compressible, and therefore you should expect that that may help to explain the experiment. And for that matter, you can consider potentials that are consistent of inverse power laws like this. I mean, the Lennard-Jones would be the addition of these two potentials, and maybe there you will have a better agreement with the experiment. So you have here the example, and we actually did and went and compute what is the phase diagram of binary Lennard-Jones systems, where you have two types of diameters and also two types of interactions. And the A-B interaction would be just the arithmetic mean. Then the phase diagram depends on all these many parameters, but let me tell you that what will happen when you put 0.6, you know, and then you have here this other parameter at 0 temperature and 0 pressure. That's not a big restriction. And it looks, you know, on a first look, it looks that you have some successes. You have sodium zinc 13, which is something that the experiments have found. You have also aluminum boron 2, which is another thing that the experiments have found. So that looks like a good thing. But then when you realize that you also predict a whole bunch of other phases that have never seen in the experiment, and those are the phases that we predicted for the phase diagram of the binary Lennard-Jones system. Not only that, you are introducing a new parameter, I mean this parameter here, and then you have the job of relating how this parameter relates to the properties of the nanoparticle. So then what you are left with is a situation where, you know, I mean, what do you do with that? Yeah, I mean, obviously the reason why we study the Lennard-Jones is not just to explain the phase diagram of nanoparticle superlattices. There are many other motivations why this study is interesting, but in what respects to investigating the phase diagram of the superlattices, at the end, this is not helping, yeah, because we have a whole bunch of other phases that they've never seen, and also, you know, how can you tell? Yeah, I mean, it's not great, yeah. Going a little more, I mean, about this idea of using kind of more flexible, like tennis type particles instead of billiard balls. You can also compute packing fractions for inverse power laws. I mean, you expand the range of stability a little bit, but at the end of the day, you know, this is another experimental result where they computed what is the packing fraction for this particular superlattice, lithium-3 bismuth. And then this is the hard sphere prediction, and this is where the experiments are. So you can see here that, I mean, you know, you can play a little bit with the parameters, but you are not going to be able to leave that curve from this point to this point by doing an honest calculation where you add a little bit of compressibility to the nanoparticles. So at the end, the predictability of just doing tennis of soft spheres is basically the same of the predictability of hard spheres. And in general, the predictability is not a lot. It's very qualitative in the sense that you are not able to predict which phase you will see. You just have candidate phases. And even if you see that phase, for example, aluminum boron 2, you are not able to predict what are the physical properties. For example, the packing fraction is wrong, the lattice constant is wrong, and so on. So the question is, how do you move from there? And it was clear early on that trying to play around with potentials, pair potentials, was not going to get us very hard. So we started looking at other ideas. And the idea here is that what we have is let's assume that you could have a situation like that. So you have here a nanoparticle, and these are the grafted ligands, and this is another nanoparticle, and here the other grafted ligands. And then let's assume for whatever reason that these ligands here are still stretched. Here you can see here that if you draw a vector, they are just all pointing outwards. But somehow in the other case, they are not stretched. They are just have a projection of these ligands to the sphere. Let me tell you that in general, if you think that if these ligands could consider exactly rigid, this would be an exact realization of an ischemia, which is the covering of the sphere. Is an application of S2 to S2, which has non-trivial topological numbers. I mean, these ligands are a little bit flexible, so it's kind of a soft skirmish. It's not exactly a perfect topological object, but it helps to think this way. One thing that I want to say is that when you have a situation like that, then what you have here is just a projection of a two-dimensional points. So what you have is plate configurations, and so the projection of this plate configuration ends up being a vortex. And if you think vortices on the sphere, you will think that there is a topological number, but this is not the case here because those are not really two-dimensional order parameters, they are three-dimensional order parameters, so they can escape through the third dimension. What that means in practical terms is that you can have any number of vortices you want if there are domain or neutral walls, neutral lines that separate them. So here's what you have. But then what I suggested is that in general, making large number of vortices is energetically unfavorable because you have to have these domain walls and that incurs in a large energy. So I just made the assumption that the number of vortices that you can have is at maximum 6 for particles that are in 3 dimensions. In 2 dimensions, you can have a few more, but that's a different story. And then for larger, if you try to have more than 6 vortices, then what we'll have is that this will be too costly, and then the vortices are expelled. And in that particular case, you have to have a situation where there are no vortices, and this is when the nanoparticles behave as hard spheres. So basically what we have here is we have a situation where we go from softer spheres to actually a situation where in certain conditions, they can undergo large deformations. But these large deformations are not arbitrary. They are determined by these vortices, and we can exactly compute what will be the packing fraction. So just to illustrate an example, this is actually the case for magnesium zinc 2. Magnesium zinc 2 consists of 2 interconnected lattices, one which consists of a diamond structure, the red ones, and another which is a pyrochloric lattice, which is the blue ones. The red ones have coordination 4, and then according to these OTM rules that I already introduced, those can be deformed and form vortices. The blue ones have coordination 6, and therefore they should behave like hard spheres. So when you look at the packing fraction I already showed you and where the experiments are, then what you realize is that if you deform the red spheres, then you will be able to increase the packing fraction in this particular branch, the left one, not the right one. And clearly this is very consistent with the experiments because you can see that the experiments are only on the left part. And that's because, as I mentioned, those are the only ones that can create vortices. And that gives you a unique prediction in which the hard sphere branch actually is lifted, and you can have a much higher prediction. And this is what the OTM predicts for the hard sphere of this case. So what you see now is that all these low packing fraction configurations actually become very high packing fraction. Not only that, it only happens on the left one, because on the right one, you cannot deform them. They are behaving as hard spheres, and that's exactly what the experiment sees. Now, the next thing we can do is that we can just go and look at this plot. Here what we have is we have the hard sphere prediction. Here is the experimental data, and then when we compute the new packing density, and there are no fitting parameters here, everything is determined, we get the result where we are able to exactly match what the experiment says, except for one point. And when I got this, I immediately contacted Dimitri Talapin and Michael Bowles, and I said, look, I have a problem with gold copper. Do you know what is happening here? And they immediately told me, oh yes, we know. I mean, what happens here is that for these lattice, what we have is that the ligands, I mean, this happens for lead sulfide nanoparticles where the ligands are very softly attached, and then under washing it many times, we lose them, and therefore so then what happens is that this corresponds to a different type of assembly, which is not driven by the ligands, but it is driven by the actual washing and the fact that the nanoparticles move face to face. So, I mean, that was a big success of the prediction in the sense that I could predict all these ones except that one. That one happened to have a different effect. There is a paper that they published later about how this happens. Actually, going back to this example, I mean, this was the prediction of the hard spheres. This is the experiments, and now when I introduce the OTM, then I get that I'm able to get exactly what we anticipate. So this is actually good news. I mean, it shows that OTM is able to predict the correct physical properties for any given phase. So I mean, if you just come to me and say, okay, I have this phase, I mean, this is a binary phase, or you know, we could do other, and I want to know what is the lattice constant, what is the density, et cetera, I can do the OTM, and so far this has proven correct. There is another aspect, which obviously I would like to answer, which is how about predicting phases? I mean, the thing is, if you give me two types of nanoparticles, I would like to tell you what type of phase you will find. Is it going to be sodium zinc 13, aluminum boron 2, or something else? Yeah. So I'm going to leave that question open for now. I will come back to this, but you know, let me move on. And I will mention these things later. Okay, so I would like to mention also a little bit about the kinetics. I mean, those are kind of complex systems. And I would like to understand how the approach of equilibrium happens. And for that, I would like to start also with a little bit more geometry. So here what we have is a perfect triangular lattice. And here what we have is we have a point which is 5 coordinated. This is a disclination, a +1 disclination, or a point that it is 7 coordinated, which is a 7 or -1 disclination. And you can also have a dislocation, which is a tight bound of 5 sevens, but that's not so important. The question is it possible to have a lattice where all points are 5 coordinated instead of 6? And the answer is yes, it's possible, but you have to work in 3 dimensions and allow for the system to have curvature. And this is what you see. So an icosahedron consists precisely of you know, 12 points that all of them are 5 coordinated. Why I'm mentioning this is because if you just, the process by which you go from here to here is the buckling, and the process of going from here to here is the decurving. So how do go? These processes are the inverse one of the other. The reason why I'm mentioning that is because when you try to do the same idea of a triangular lattice in 3 dimensions, which would be the idea to tile the space with tetrahedra, you start realizing that you form these little gaps, so you cannot succeed. In a way, what happens is that this is a frustrated system. You can follow the same idea though, and just work in 4 dimensions, and then being able to curve this 3-dimensional structure into with curvature, and then with that you are able to form this structure which has 120 of these tetrahedra, and is the 335 polytope. This is actually a conformal projection. So here you have to sacrifice something in order to be within 3-dimensional space, and you sacrifice the distances. But you can see that this structure is made of tetragonal so of the perfect tetrahedra that if we were able to visualize in space, 4-dimensional space, would be perfect tetrahedra, all of them. So you will be able to tile this space by these things. The reason why I'm bringing this up is that because in order to do the decurving, in order to go from this curved surface to a 3-dimensional space where we don't have curvature, you can do it through disclinations. And the disclinations that are allowed in this system, this is fixed by the symmetry group, are 2π5 disclination and 2π3 disclination with different charges. And then if you just use the -1 2π5 disclination, you can decurving the 335 polytope, you get the magnesium zinc 2, and this is what is called the Frank-Casper phase. So basically the curving the 335 polytope with only this type of disclination gives you the 335 polytope. But we don't have to restrict ourselves to just this type of disclinations. We can also use the other ones. And when you do, you get the aluminum boron 2. Here you have, this is the disclination network, the gold copper 3, the BCC AB6, or the sodium zinc 13, which consists only of 2π3 disclinations. And in this way, you are able to see that all phases that have been reported experimentally actually happen to be networks of disclinations from the 335 polytope in what we could call quasi-Frank-Casper phases. So in a way, the 335 polytope is kind of the mother of all superlattices, in a way that if you start with this by adding disclinations, you can build all these other cases that experimentally have been found. So with that, I will mention a little bit of experimental evidence on that. So what we were able is to adjudicate a certain amount of icosahedral order to each superlattice. And then the experiment, what they found is that the phases like sodium zinc 13 or calcium copper 5, which have high level of icosahedral order, they form very quickly, and they form small fragments very quickly, while those that have very small amount of icosahedral order, like lithium-3 bismuth, those actually form single crystals, which are very hard to nucleate. Yeah, and this is actually what the experimental evidence that provides some evidence that this presence of icosahedral order has implications for the dynamics of the system. There are a few more things. These are also related to glasses. I mean, this is not a topic I'm going to describe here, but I mean, it's actually an interesting connection. So basically what I've told you so far in the summary of theory is that we have hard spheres. We try to make a model with soft spheres. And then this is not enough. And actually what really need in order to be able to predict what are the physical properties of superlattices is the introduction of these textures, vortex textures. And then you have this model, which is able to really explain the lattices without, I insist, having any type of fitting parameters. The other aspect I've said is the importance of the 3-3-5 polytope and icosahedral order, and how phases are basically end up being quasi-Frank-Casper phases with a high degree of icosahedral order. So this is actually where we are. I mean, one thing that I want to mention is that so far I haven't done any numerical simulations. So this is where I'm going next. I mean, back in the time, I mean, many years ago, we started developing WhoDLT, which is a program that allows you to do all these calculations. So if you really want to check these calculations and you don't want to do all these complex calculations about the packing fractions and all these things, we have this code where everything is implemented. It also has calculations for free energies. It also has a huge database of nanocrystals that allows you to do all atom simulations in combination with WhoMD, which is another code that we developed a long time ago with my former student Joshua Anderson. And you know, those are things, and then these two codes work together. I mean, WhoDLT has not been released to the public. It was almost about to be released, but now we have WhoMD 3.0. So I'm working on adapting WhoDLT to work with WhoMD version 3.0, and then with a few more modifications in regards of the documentation. We will be able to release it to the public. If someone wants to use WhoDLT to calculate packing fractions or whatever you want to do, or do all atom simulations, as I will describe in the following transparencies, I'm more than happy to share it. I've been already sharing it with a few people on a personal basis. So one of the calculations that we've done is, for example, the characterization of many body effects. So many body effects is, for example, a situation like that, where you take 6 nanoparticles and 1 particle. So you have a coordination 6 nanoparticle, the one at the center, and then you approach the nanoparticles closer and closer, and then you compute the free energy as you approach the nanoparticles closer and closer. And then what you do is you compare what is the free energy of the system with the free energy of just if the particles were interacting as pair potential, that is through the potential of mean force. So you start with n equal 2, so that would be just 1 particle at the center and 2 at the end. You get something like that, and you see that the potential, the sum of the potential is basically the same as the free energy. When you put 3, the situation is closed, but you start seeing some differences. With 4, you start seeing significant differences. With 5, you start seeing bigger difference, and with 6, the difference become even more important. The point here and this, you get a situation like that. So the point here important is that this plot here, which is the difference between the actual free energy and the free energy that you would get if you consider the potential to be the sum of 2 body interactions. That is, you compute the potential of mean force, and you compute that this particle interacts with this one separately. You sum all the potentials, and you see that there is a huge contribution that comes from 3 body, 4 body, etc. So what this shows you, many body effects are actually very important. You can see here that the separation between nanoparticles increases with coordination. That's another manifestation of many body effects. And in fact, if you plot the separation in terms of some unitless variable, you see that the higher the coordination, the farther the particles are. This completely agrees with the experiment. And this line here represents what would be the Hart sphere. So here what you see is that at coordination 6, basically, you already are in the Hart sphere limit. So that's when the particles behave as Hart spheres. This is when you have vortices. Then when they become Hart spheres, you have no vortices. That would be what we call the OPM. Okay, so we have other calculations that we've done. Here, for example, we have a transition from the FCC to icosahedron order, just providing even more evidence. This is an example of vortex coalescence, which is actually how many body effects arise. And here I would like to show you what happens if you have a tetrahedral. So here you have a central nanoparticle surrounded by 4 nearest neighbors. And then you start approaching these nanoparticles together. And then what you see is that at the situation where they are at the minimum of the free energy, you see that the particle at the center has this configuration, which is 1 vortex, 2 vortex, 3 vortices, and 1 vortex behind. So they form the 4 vortices that we expect. And the particles that are actually in contact, they have just 1 vortex because that's the one they are here. So here what we show is with an all atom molecular dynamic simulation, the presence of all these vortices. What happens if you do the same thing now with an icosahedron? Well, in that case, you have a coordination 12. And you have that the particles outside, they do have vortices, the particles that are outside, but the particle in the center doesn't have any vortices. The vortices are expelled. So some of these are a little bit tilted, but they are all straight. And therefore, what we show is that the particle at the center, in this particular case, is behaving as it should, as a Hart sphere. So what we see is that with these all atom molecular dynamic simulations, we are able to show that indeed these particles behave as Hart spheres when they do, and they behave as with vortices when they should. The next thing that we looked at is we looked at what happens with single component superlattices. So we form BCC and FCC structures. So we compute the pressure, and then by integration the pressure of the volume, you compute the free energy, and we compare what is the free energy to the to the sum of the pair potentials. And you can see here that in general they agree fairly well, because basically here the nanoparticles are behaving as Hart spheres, and therefore they are well described as two-body interactions. And there are here a few calculations for chain, square, hexagonal, BCC, FCC. You see that in general, for short chains, you form a FCC structure. For longer chains, it becomes more like BCC, although the precision of the calculation is not, let's say, amazing. There is also another effect that has to do with the BCC, which basically the BCC and the FCC for these systems end up having the same packing fraction. And this is something I'm not going to describe in detail, but basically, the results are in good agreement with the experiment. And I mean, this transition for FCC to BCC, we are not the first to find it. I mean, it was already described by Lutke and Landman many years ago for single component lattices. When you go to polymers, I mean, there is a situation where, there are many things that happen. For example, when you have long polymers, the nanoparticles are able to form the two-body interaction. The main field is actually quite complex, because when the polymers are sufficiently long, they can form this type of structure that we call the cascade effect. The free energies follow more complicated formulas, but at the end, I mean, those are also can be successfully described by the OTM, even though at the end, I mean, even for very long polymers, this corresponds to nanoparticles that are functionalized with polystyrene. The free energies are I mean, the same aspect, and we can even identify vortices. When the chains are short, we get the usual vortices, but then as you start going larger, they become a little more complicated, but at the end, they follow the same procedure. So even if you go to the polymer limit, they are also well described this way. So, I mean, the OTM is accurate also, and it works within simulations, yeah? And when we go to binary superlattices, then, well, here we have the pressure, the energy, and again, that's how we compute the free energy. And the minimum of the free energy, this computes the lattice constant. This is the prediction for OTM, and this is the prediction for hard sphere. So you see how well the OTM predicts the actual lattice constant in simulations. And then here you have it a little for magnesium zinc 2, which is the lattice I've been using to illustrate the point. You see here how well that this is the type A, that those are the ones that have formed vortices, how well are described with the OTM model, while the hard spheres are kind of quite a lot off. If we take a look at the actual simulation, we can see here what this looks. This is the diamond structure of the large A particles that form magnesium zinc 2, and you can see here the presence of the vortices. You know, in both cases, you can even look a little more closely, and you can take these things and then put here the OPM. The OPM is the hard sphere diameter, and you can see how the hard sphere diameter overlaps. And this is well described, extremely well described by the OTM. Here you have the OTM. So you see how the distance between these two particles follow the OTM. By the way, if I take an FCC lattice like formed by these nanoparticles, the separation, then it's something that looks like this. And you can see here how the hard sphere describes very well where the nanoparticles are. So this is another verification of the prediction of the OTM. We see that for coordination 4, which is the magnesium zinc 2, they form vortices. And for coordination of 12, which is FCC, they behave as hard spheres. So this is actually an example. I mean, another demonstration using numerical simulations that the predictions for OTM actually are satisfied. And this is true for magnesium zinc 2, but it is also true for all the binary superlattices that we've looked at. And we've looked quite a bit. In this paper, you can find all the details. So where I am, I've been able to show you a summary of theory that we started with hard spheres. We went to soft spheres. That didn't really help that much. But at the end, what helped is the OTM, the icosahedral order, and the quasi-Frank Caspar phases. And here what I've done is that by looking, and I've done extensive comparisons with experiments and simulations, as of March 2022, we are the theory is as good as it gets. I mean, we haven't had a single case of a discrepancy with this theory. So in the time that I have left, I would like to go beyond spherical nanoparticles. And I would like also try to introduce, or at least describe, the importance of these superlattices. Why do we care about these superlattices, and in what sense these superlattices have functions that are interesting pursuing? In a way, what are the properties of these materials? So one way to go beyond spherical nanoparticles is a topic that is of big interest, which is cesium lead halide perovskite. In general, perovskites are semiconductors, and they have lots of interesting properties. So for example, I mean, this is an example of a nanocrystal. This is a big one. You know, well, not a big one. It's you know, reasonably size. I mean, it's 10 nanometers. I mean, if you just have single cube like that, they form super lattice, which is a simple cubic. Yeah, just a simple cubic lattice. And they have very nice properties, interesting properties. So for example, they are tunable band gaps. So those are semiconductors, and the band gap is in the visible, and you can tune it in such a way that you cover the entire visible spectrum, going from the blue to the red and anything in between. They are also extremely good at power conversion efficiency. I mean, they have efficiencies which are very high. So they have a lot of very nice properties. And another property that they have is the property of superfluorescence. So let me tell you a little bit what this is, because I will come back to this soon. So the idea is that you have a photon in, and then when you have a photon in a semiconductor, what you form is an exciton, that it is a hydrogen atom, which consists of an electron and a hole. This electron and hole have a final lifetime, eventually decay, and they emit another photon. That's what you have. So photon in, photon out. However, when you put these nanocrystals in a superlattice, something interesting happens. When you have photon in, it doesn't decay automatically, but you form a coherent state where nothing happens, but all of these excitons become in phase. And then eventually they radiate, they decay, but they decay all at once and emit a superfluorescence pulse, which is something that you can see here. What is important here is that this only happens when you put these nanocrystals in a simple cubic lattice. It doesn't happen when they have them in some amorphous type material. So we looked at what happens with these perovskites and how to assemble them. Here we have an example of our early work. Those are typical superlattices. There are different types of ligands that you can put. And this is what it looks like. And we've done simulations. And here what you see is that in general, if the density of which you grab them is very high, you still develop vortices around the corners, but in general, the center behaves as a hard group. So here, even in a very high packing fraction, in a high packing of the ligands with the cubes, you can form what it is, a very hard cube, but you will also be able to form vortices at the corners and even at the edges and so on. So with that, let me tell you what the experiments tell us. This is work in collaboration with the group of Maxim Kovalenko. So when you have these 8.6 nanometer perovskite cubes or 5.3 nanometer cubes, and you combine them with spherical nanoparticles, something that looks like that, then you have a parameter, which is this gamma parameter, which is the equivalent that you had for different type of binary spheres. And what you form is you form these phases. So you have sodium chlorine, AB2, aluminum boron 2B, AbO6, and BaBO3. So you have these many new phases where it's not just the position of the cubes, but also their relative orientation. And we have computed the packing fraction for all these things, and I will come back to that. You can also play with truncated cubes. And then when you combine the cubes with truncated cubes, then you get these other phases, BaBO3, sodium chlorine, gold copper, aluminum boron 2. When you put, you can also even make ternary phases where you combine spheres, cubes, and truncated cubes. Yeah. Then you also, the group of Maxim Kovalenko is able to have sodium gadolinium fluorine disks and also lanthanum fluorine 3 disk, and then you get a whole bunch of new discotic and also cubic phases like this. So this is actually the current state of the phase diagram that we have for combining things with different shapes. Yeah, so that there is cubes, there are disks, and then there are truncated cubes, and there are spheres. So this is actually the system. Most of these are binary, but this is actually happens to be ternary. So what we do here, as usual, we already know what are the rules. We first consider the hard sphere, and then we see in which situations you will have the presence of vortices. And then based on that, we will predict what is the packing fraction. And indeed, we concentrated, for example, for these two types of superlattices. And for this type of superlattices, what you have is that those are the structure. The aluminum boron 3 has these cubes here, and there's another cube at the center, and they are tilted, rotated, and the sodium chlorine is the type of sodium chlorine that you expect. And then when you compute the packing fraction, what you see is that in general, for hard spheres, it doesn't quite work. But when you include the presence of vortices, as you have here, in the corners, as I already anticipated, then you are able to see that the packing fraction is greatly enhanced, and therefore you can tell and predict what are the lattice constant and with it for these perovskites.
Alex, can you come to an end within a minute or two?
Sorry?
Can you come to an end within a minute or two?
Yes. And I just want, I'm almost there. So I want to mention here, again, going back to superfluorescence, I already mentioned what happens here, the fact that these excitons decay all at once and emit superfluorescence. And this happens for AbO3, but not for sodium chlorine. This actually tells you something which is very important, which is that the structure determines function. I mean, sometimes people ask us, why do you care about superlattices? Well, the answer is the optoelectronic response of these superlattices is different than if you have these nanoparticles in an amorphous structure, or it is different whether you have AbO3 or sodium chloride. And there are many other examples of the collective properties of these superlattices, but this is just one of them that I want to emphasize, and that in a way justifies why we put so much effort in these superlattices. So now I'm going to try to finish on time. So those are my conclusions. One thing that I want to say is that these nanoparticles, sometimes they behave as hard spheres, sometimes they behave as flexible by these large deformations, but in either case, we can always predict what happens because they follow these OTM models I introduced. There is a universal tendency towards icosahedral order, and we have already proved these things. I mean, not just from theory, but also from simulations, and then by comparing with a large number of experimental systems. So I would like to finish here with some open questions as the idea of the talk gives. So I would say that OTM solves so far the problem of predict the structure of a given superlattice. So if you come with, say, magnesium zinc 2, and you tell me, you know, okay, then I will be able to tell you, with given the properties of this nanoparticle, what is the lattice constant, the density, and the structure of the ligands. I can predict a lot of things. The other question that you would like to answer is predict the equilibrium phase. So the idea is that you come with two nanoparticles and you say, okay, if I put these nanoparticles in toluene and I evaporate the toluene, tell me which phase I should find. And to this question, at this moment, I cannot answer. And I don't think anyone can answer. You know, it's an open problem. I will say a few things that we learned from our studies. The first one is that the pair potentials will not work. I mean, we already mentioned that there are many body effects. So if you just try to put a very sophisticated two-body potential, the chances that it will succeed are very thin, because we've already shown that there is a dependence, for example, on coordination. And that means that it depends on how many neighbors you have. That means it depends on how many particles are interacting at the same time. So pair potentials have very little chance to work. All atom free energies, I mean, this is something I haven't talked much because the free energies of these systems happen to be extremely close. We have calculated free energies, but the difference between two-phase separated single component lattices and a binary one, it's extremely close. And with the precision that we were able to calculate free energy, we could tell which one wins. And there are better, I mean, it's possible that there are more accurate ways to calculate free energy than we did, but still, I mean, the free energies are very close. And that raises another question, which is that effects that are subleading, that has to do, for example, for dipole interactions, it has to do with core-core interactions and many other effects that in general, when you put numbers, are not important. When the free energies of these two configurations become so close, then all these subleading effects start to become relevant and could actually drive the equilibrium in one case or another. So that makes it even more harder. How are you going to be able to surmount? So just to finish on a positive note, maybe mean field models have a better chance that that free energies calculated by all atom simulations. Maybe there are some hidden correlation, machine learning could help there. Anyone? I don't know. But I mean, this is an open question, and one that at this moment, I don't think anyone has a real solution, but it's an important one because we would like to be able to design things in the laboratory and tell the experiment what are the conditions in which they will find a given phase. And with that, I'll finish here and I will entertain questions.